All right, so antiderivatives. We're going to do derivatives backwards. Antiderivatives are also sometimes known as, indefinite integrals. And next quarter, we'll get more into what an integral is. It's the reverse of a derivative, is one idea about it. And so the way antiderivatives work is it's a guessing game. I took the derivative of some function, and the answer I got was x to the 7th power. What did I take the derivative of? Well, let's see. I remember the power rule, right? And what the power rule told me is that if I took the derivative of x to some power n, the answer should be n x to the n minus 1. So based on that, I can build the function I want. So let's see. When you take a derivative, it drops the power out by 1. So reversing that, I should increase the power by 1. So whatever this is here has to be some relative of x to the 8th. When I take the derivative of x to the 8th directly, don't I get 8x to the 7th? Yeah. So I'm a little off. I don't want that 8 to be there. How do I get rid of a multiple of 8? 5. I would divide by 8. So if I divide by 8 over here, then this function should have the derivative I want. Try another one. Yeah, that's interesting. Yeah, so let's try another one. Page. I'm going to take the derivative of a function, and the answer I get is 12x to the 11th power. What did I take the derivative of? X to the 12th. Let's see, x to the 12th. Check your guess. The derivative of x to the 12th is 12x to the 11th. Check. Yeah, so anytime I do an antiderivative, I take the derivative to prove myself I got it right. Let's try another one. I take the derivative of something, and I am going to get a 5x. So let's see. Reversing the derivative, I have to increase the power. So it has to be something about x squared. Well, 5 is a constant multiple, so there probably was a 5 there also. If I take the derivative of that, what do I get? Well, I'm going to get 2 times 5x. Not quite what I want, so how can I adjust? Divide by 2. Yeah, so if I divide this by 2, then I get the 5x I want, so there must be a divide by 2 there also. So this should be the antiderivative of 5x. Okay. So let's try to do it in general for powers. So you're just doing it in reverse. Yeah, so I know that the derivative with respect to x of x to the n is n times x to the n minus 1. So I want to reverse that. So the antiderivative of n x to the n minus 1 is just x to the n. Now, what I'd rather have here, I'd rather have this just be the x to the n here. So I got to tweak things to make that happen a little bit. So if instead of an n minus 1, if I want that to be an n, I should probably increase by 1 all of these n's. So I could rewrite this by saying if I increase that by 1, that's an n. This then becomes an n plus 1. And over here, this is going to be x to the n plus 1. So I'm just increasing everything that was in n by 1. And then I'm going to get rid of the n plus 1 on this side by dividing it to the other side. So x to the n, this becomes n plus 1 over n plus 1. So now I have the antiderivative.
X plus 1.
N plus 1.
Oh, X plus 1.
Yeah, you throw x plus 1.
So the antiderivative of x to the n, oh, right, n, sorry, gotcha. N plus 1. Yeah, so, and this kind of makes sense. When we take a derivative, the order of operations is bring down the power, then increase it by 1. If I reverse that, I want to increase the power and then divide by n plus 1. Opposite operations, just reverse everything.
And then the constant multiples also just.
Constant multiples just carry along, yes, just like they do in differentiation. Yeah, okay, so I'm going to give you a slightly harder problem and see if you can come up with the antiderivative. So the derivative of some function is 3x minus 7. Come up with the function that I took the derivative of. So it's kind of, you can do a guess and check, or you can apply this formula here where constant multiples hang on. Then take the derivative of it to check. If you take the derivative of it and you get the same thing, then you must have picked the right antiderivative. That'll be my take on it. So my take on it is this 3 here is a constant multiple, so it just hangs on. This is, I could view as x to the first, so I want to increase the power by 1 and then divide by that power. Minus 7. Well, I get a constant derivative if that was a linear function, so that must be 7x. What's the derivative of negative 7x? It's negative 7. What's the derivative of 3x squared over 2? Well, that would be 3 times x squared times, x times 2 over 2. Yeah, and that derivative is just 7. The 2's cancel, and I have back what I started. So that's my check. And again, antiderivatives, we work so hard on derivatives, we got those down. Antiderivative are backwards. I generally have to take the derivative, at least in my head, to make sure I get the right antiderivative, because it's easy to make a mistake. It's a little more work than the others. So this should be the antiderivative. So it's nice to have a rule. So we have an antiderivative power rule now, which is nice. But there's a lot of other ones we just have to remember. So other rules are based on things we learned before. So for example, I just have to know things like the derivative of the sine is the cosine. So then the antiderivative of the cosine is what?
Sine.
Yeah, just a sine. Antiderivative of cosine of x is the sine of x, not the negative sign, it's just the sine. I know the derivative of the cosine of x is the negative sign. So reversing that, the antiderivative of the sine of x would have to be what?
Negative cosine.
Negative cosine. Yeah, the negative switches when we take it the other way. All right, I'm going to jump straight to an antiderivative, see if you can tell me the answer. The antiderivative of secant squared is, yeah, because the derivative of tangent is secant squared. How about antiderivative of secant of x times the tangent of x is, what trig function had that derivative?
Like cosecant.
Not cosecant.
Yeah.
Cosecant has a negative.
Yeah.
Nope, not the cotangent. That would be negative cosecant squared.
The secant.
This is the, yeah, that's the, yes, the derivative of the secant is the secant tangent. So the antiderivative of secant times tangent is secant. Okay. And again, that last one is because the derivative of secant of x equals the secant of x times the tangent of x.
The always confusing.
Yeah,
secant
so-
of-
Yeah, there, and again, if you don't have them memorized, you got to look it up. So to answer some of these questions, you're probably going to have to go to a derivative table. There's one in the book. If you search online, you can get a list of derivatives. I gave one the other day. I'm going to take the derivative of a function, and the answer is 1 over x squared plus 1. No,
Natural log.
Not
That's
natural
the-
log.
That's the cotangent.
nope, not the cotangent.
Arctan.
Arctan,
yeah,
or
yeah,
inverse
arc-
tan, yeah.
That's
So,
what I
yeah,
meant to say.
So if I put tan inverse here, which is the same as the arctan, yeah, so this is one of those where you can't use, you got to know it or you don't know it. Right. Okay, here's another one. Derivative of what function is 1 over x?
ln of x.
Natural log of x, yeah. So the antiderivative of 1 over x is natural log of x. So it turns out the power rule doesn't work on 1 over x. Let's check that out for a second. So if I look back here at my power rule, the power rule says increase the power by 1 and divide by that power. Well, 1 over x is x to the negative 1. And if I add 1 to that, what do I get? Over 0? Doesn't apply. Yeah, so that doesn't apply if n is negative 1. Doesn't work. We just have to know it's the natural log. Yeah. Okay. Sometimes you can't easily find an antiderivative. So if I said I took the derivative of some function and I got cosine of x squared, we cannot easily solve that. If instead I said I took the derivative of a function and I got the cosine of x squared times 2x, then we can actually solve this one. Anybody want to guess? What's an antiderivative for cosine? Sine. It's got to have an x squared in there. What happens if you take the derivative of that function? The chain rule says take the derivative of the outer, derivative of sine is cosine, and then multiply by the derivative of the inside, which is 2x. So I'm done. Since this one up here doesn't have that 2x, I can't just guess at it. And next quarter, we'll learn some tricks to how to deal with that. And sometimes there is none. There's no function you can write down that is the answer. I can't remember if that's one of them. For sure, if we were trying to find an antiderivative for the sine of x over x, doesn't exist. Not in terms of functions we know of at this point in our life. Doesn't exist. And we'll talk about that next quarter some more. Okay. So the problems in this are going to reinforce what you remember about derivatives, because there's going to be some that aren't obvious and you're going to have to look it up somewhere. And there's a derivative table in the back of the book, or you could search online for a derivative table, and then you get a list of things like derivative of the arc tangent, derivative of the arc sine, things like that that aren't don't come immediate to memory because we don't use them a lot. All right, and that's it.
Does the derivative calculator do antiderivative?
There is an antiderivative calculator out there. So actually, I might as well show that before I stop the recording. So earlier I said there's another name for antiderivative, and it is called where is it? Indefinite integral. So it turns out like there's a derivative calculator online, there are integral calculators online. And you can feed them a function and it'll tell you what the antiderivative is. So let's just demo that here, see how it works. So I'm just going to search for integral calculator, integral calculator. And this was written by the same guy who wrote the derivative calculator. I like it. There's other ones out there. Whoa. So I could type something like sine, no, what I had before, cosine of x squared, and then times 2x. And it writes it using, this is the notation for indefinite integral. The boxes are above what are called a definite integral. We'll get to that next quarter. And it should come out with sine of x squared. Notice I put a plus c there. C stands for constant. Yeah, because the derivative of a constant is 0. The original function could have been +1, +2, plus pi. I don't know. So one thing is when we take derivatives of functions, we lose information. Like if there was an added constant, we lose that information. Okay. Oh, I need to show an example of that, and then we'll be good. I'm going to do that in a second recording here.